Traditionally, most socket application uses the socket API. For example, connect, accept, send and receive, all are functions that are used to pass data from one point to another. RDMA programming is an alternative to socket programming. It gives you better latency and better utilization of your hardware, if you have network interface cards that can work with it. RDMA programming relies on the following three concepts. The first concept is transport offload. When you are sending a packet from point A to point B, there is inherent overhead. The operating system must fill in network headers and pass the data from the user application to the hardware so it can be sent. In contrast, in RDMA programming, transport offload means that the overhead is passed from the operating system to the dedicated hardware. Essentially, this takes the latency away and makes the transfer more efficient. Now, the second concept is kernel bypass. This means that when data is passed from the user application to the hardware, it doesn't have to pass through the operating system. And the third concept is RDMA operations and atomics. These are specific hardware-based operations that allow you to pass data more efficiently and faster between 2 points. How do socket applications work? So first, the application wants to send data. So it passes the buffer to the socket library. The socket library then calls a system call, passing the buffer to the operation system. There, the TCP stack passes it down to the device driver, which eventually passes it to the hardware, which finally sends the buffer on its way. In RDMA programming, the application passes the buffer to the RDMA library instead of the socket library, which passes it directly to the hardware for it to be sent. The operation system is not involved in this process, which means it will happen significantly faster. This does not mean that we don't have device driver with RDMA. We do have them, and they are used for operations like a resource allocation and connection establishment, which typically happen once or maybe twice in the beginning of the application. So they are no longer used from that point on. This means that the data path or the path that the data passes through to get sent doesn't go through the operation system, while other operations like connection establishment do. We call this part the control path. So let's continue and learn about what exactly RDMA is. And to understand RDMA programming, we must first talk about communication models. Now, the first most common communication model is two-sided communication. And in two-sided communication, we have a sender and we have a receiver. When data is sent from the sender, the receiver accepts the data and places it in a specific spot in its memory. Another communication model is the one-sided communication. In the one-sided communication, we may have the same sender, but the receiver will not participate in the operation. Okay, so the sender will send the data, but the receiver will not need to be involved. The data will be placed directly in its designated memory space. RDMA stands for Remote Direct Memory Access, meaning there is a hardware capability that supports the one-side communication model. Okay, so we still have the sender and the receiver, but when a message is sent, it already has a destination address. So the hardware on the receiver side directs the message to its specific address. RDMA programming usually uses the one-side communication model. Okay, the receiver will remain inactive and uninvolved, making the one-side communication model more efficient. Now, a very important concept in RDMA would be memory zero copy. When using the one-side communication model and the RDMA capability, we have two common techniques for sending data from one point to the other. The first is called the buffer copy, and the second is called zero copy. Buffer copy means that you have a temporary buffer or buffers on both sides of the sender and the receiver. When the application wants to send a big buffer full of data, the data is first broken down and copied to those buffers, the buffers on the sender side. Now the sender then sends each buffer to the corresponding buffers on the receive sides, and those buffers are eventually copied to the destination in the remote memory. Zero copy, as its name suggests, well, tries to make the few copies as possible, hence zero copy. When the sender wants to send a big buffer full of data, it notifies the receiver of its intent without actually sending the data. Only once the receiver is ready and responds back to the sender with a reply message, then the sender knows it's ready and transfers the data using RDMA. Remember, with one-side communication, the sender, once it knows where the destination memory is, can send directly without the receiver being involved. Zero copy can work both ways. It can work from the sender to the receiver or from the receiver to the sender, depending on who is ready first. When the sender has the buffer ready, it notifies the receiver. If the receiver knows the buffer is going to arrive beforehand, the receiver may start with notifying the sender where the destination memory is. In this case, when the sender is ready, it already has the destination address and uses RDMA to transfer the data. In comparison, a buffer copy uses a send operation like the two-sided communication model we mentioned earlier, while the RDMA uses the one-sided communication model to achieve zero copy, means no copies on the destination side. Also, the overhead of the first method, the buffer copy, is significantly higher because of those additional memory copies on the receiver side. When we're talking about the optimal message size with buffer copy, we're targeting the small messages that can fit into one single buffer. When we're talking about large messages, we're much better doing it with RDMA. So, to sum up, we have buffer copy, which uses temporary buffers on both sides and an additional copy operation. And we have a zero copy method, which means the data is transferred directly to the destination address in the remote memory. Moving on to transport offload. So, to better understand RDMA, we need to go over the responsibilities of the transport layer. The transport layer has three main characteristics. First, we got to ask ourselves whether the transport is reliable or unreliable. Okay, or when we send a message using this transport, does it guarantee the arrival on the other end? Second is connectivity, or is the transport connection-oriented or a connection-less transport? Okay, do we need to establish a connection to use this kind of transport? And third, is it message-based transport or is it stream-based transport? Okay, does a single message stand on its own when it's sent, or is the connection a constant flow of data from point A to point B? For example, TCP, which is a commonly used transport, is a reliable transport. It means it guarantees the arrival to the destination. It is also connection-oriented. It means that we need to establish a connection with the other side before we use this transport method. Okay, in contrast, we got UDP, another commonly used transport mechanism, which is a connection-less, okay, and also unreliable transport. It means that it can send every message to a different destination without establishing a connection, but it does not guarantee those messages will arrive at the other end. So, how does reliability actually work? Reliability means that every sent message will arrive at the other end. If a message does not arrive for any reason, we will be able to tell, because the next message will arrive and we will indicate that the previous message did not. For example, if we have 3 messages sent and only message 1 and 3 arrive, it means that message 2 is missing. Okay, the receiver will then notify the sender that message 2 is missing and needs to be resent. When the sender receives the notification, it retransmits message 2. This way, all the message will eventually arrive at the receiver's side. Now, for various reasons, not all messages and notifications arrive after being sent. And for those cases, we have another technique called timeout. So a timeout is a specific period of time where we expect a message to arrive. If we don't see the message, we retransmit it in order to get the message to the other side. Here's an example. Let's say message number 1 is sent, but the acknowledgement, the fact that it arrived, did not reach the sender. In this case, the sender will retransmit message number 1 in order to make sure that message number 1 actually arrives at the remote end. RDMA programming has 2 types of transports: RC, which stands for reliable connection, and UD, which is unreliable datagram. RC, as its name suggests, is a reliable connection-oriented transport. It means that every sent message is guaranteed to arrive to the other side, and you need to establish a connection before you start using this transport method. On the other hand, we got UD, or unreliable datagram service. It means that every message can potentially be sent to a different destination, and it is not guaranteed to arrive at the other side. Now, for most purposes, RC, which is very similar to TCP, could be used to make simple applications like client-server. UD, very similar to UDP, can give you better latency and scalability for specific use cases. Other transports are also included, but will not be covered in this session are DC, RD, UC, and XRC. Next thing we'll talk about is RDMA verbs. Verbs is the API for RDMA applications. This means that RDMA application willing to use RDMA needs to use the verbs API and link against the verbs library. The verbs API is divided into 2 sections: the control path, including resource allocation, modification, and destruction, typically involving the operation system, and the data path. This is the path where we send and receive data. It has to be fast and efficient. The verbs API focuses on performance and being as close as possible to the hardware. This promises us the best latency, bandwidth, and message rate. It's also useful for multiple types of applications, from client-server applications, the ones that we usually use socket for, and also storage, AI, and parallel computing. libIB verbs is the user space library for RDMA applications. It means that the application has to link against this library to get RDMA operations going. libIB verbs is open source and it is available for multiple Linux distributions. It also has a kernel counterpart for device drivers willing to use RDMA. Our focus will be on the user space, user level, and libIB verbs. So let's begin with verbs objects. The most important objects in the verbs API are requests, completions, and queues. Work requests are essentially requests from the application to the hardware to execute an operation, typically an RDMA operation. Now, we also got work completion that indicates the completion of a previous work request and typically contains both a pointer to the work request and the status of how it was completed. A work queue is an object that allows you to post work requests to be completed by the hardware. For example, if the application wants to post multiple buffers for sending, it will post multiple work requests on the work queue. Those requests will be handled by the hardware in the order that they were posted. However, if you have multiple queues, the order in which they were posted will not necessarily guarantee the order in which they will be executed. Now, every work request is considered outstanding until there is a work completion generated for it by the hardware. Only then you will be able to know the completion has happened and have access to the buffer, if it's a receive buffer. So a work completion will be posted to a completion queue and will be read by the software. Now, a send queue is a type of work queue that contains send requests. When the application wants to send data, it will post a send work request to the send queue, indicating it wants to send a buffer to a remote destination. A receive queue, on the other hand, is a way for the application to receive incoming data. It would post buffers to the send queue via the receive work request, and every time data arrives, it will be written into one of those buffers in the order that they were posted to the receive queue. Okay, so similar to socket, we got queue pairs, which is a receive queue and a send queue bound together. Now let's dive into data path flow in RDMA. So previously we covered RDMA API objects. Now let's see a demonstration. On the software level, we have the work requests and also the work completions. Below that, we have the verbs library level, and then the hardware level containing all the QPs and the completion queues. Now keep in mind that QPs contain send and receive queues. On the send side, we want to send two messages, hello and welcome. So first, we generate two work requests, one for each message, pointing at the location on the memory where hello and welcome are written. We post the work request to the send queue, generating two work queue entries. The hardware processes the work queue entries in the order in which they were posted and generates a completion queue entry in the completion queue for each entry. The third type of RDMA operations is the RDMA read. Like RDMA write, this is a one-side operation, but in this case, the data lies on the receive side. Now on the receive side, we don't know how much data will arrive before it actually does. So we allocate buffers, create a work request, and post it to the receive queue. This creates a work queue entry pointed at the data we allocated, and once this data arrives, the hardware places the data inside the buffer we allocated and generates a completion queue entry. Eventually, the software checks this completion queue and gets a notification that the data arrived in the form of a work completion. The work completion contains the status of the data that arrived along with additional information. So the next thing we'll be talking about is memory management in RDMA. So operation systems typically include virtual memory management. Hardware has its finite number of resources, which includes physical memory, while each process has a range of virtual memory dedicated for its use. So in almost every case, the number of processes times the size of the virtual memory for each process is much bigger than the size of the actual physical memory available on the system. For example, if we take a 32-bit system, the size of the virtual memory for each process is 4 GB. Okay, the operation system is responsible for mapping that physical memory it has to the virtual memory in the processes. Now, the user-level software, which are most applications, only use virtual memory addresses. Some of the virtual memory range is allocated and available for use, while the rest is vacant. Now, the applications can only access allocated memory. If we access vacant addresses, we get a segmentation fault. Addresses also have permissions like read, write, or the ability to execute code. When they allocate memory, the operation system takes the physical memory and maps it to a vacant space in our virtual addresses. When low on physical memory, it may come in the expense of other processes on the system. RDMA requires a special kind of memory allocation. We call it memory registration because we register pre-allocated memory. It involves the driver inside the operation system, hence it's part of the control path. Registered memory has 3 properties. The first is protection, where there is a range of virtual addresses with access permissions for reading and writing or for accessing locally and accessing remotely. The second property is memory pinning, meaning that the physical memory is locked in place. The third property is translation handle, which is used to access the memory from the hardware itself. Verbs can only send or receive to registered memory. Memory registration typically happens in the beginning of the application, and it is used throughout the run. Although memory pinning has its disadvantages, for example, taking memory from the operation system and locking it into the process, it also has advantages. It gives the best possible access in terms of latency, and pages are always present in the RAM. Now, to summarize, memory registration has 3 properties. First, protection and permissions. Second, it's the physical locking of memory. We also call it memory pinning. And the third is the handle for accessing that memory. Okay, so let's recap what we learned so far. So the 3 most important verbs objects are queue pairs, completion queues, and memory regions. A queue pair is a transport endpoint, just like a socket for TCP communication. It's a synchronized interface for sending and receiving messages. Now, if you want to send a message, you create a work request and post it on the work queue. If you want to receive a message, you create a work request and post it on the receive queue. Both are part of the queue pair. Now, the completion queue is a method for notifying us that our send or receive requests have been completed. A memory region, which is reference to registered memory. We can only send and receive messages that are registered with the Verbs API. If we look at the complete Verbs API, we can see many objects. But these 3 are the most important for sending and receiving messages with RDMA. Okay, so let's move on and learn how to send and receive using RDMA. And the first type of RDMA operation is the send operation. For send operations, first the receiver must be ready for incoming data. So it will post a receive work request with the buffers allocated for this data. Once the data is ready on the send side, the sender will issue a send or a work request, and this will get the data sent on the wire and to the receiver. When the data arrives on the receiver side, it will be written to those buffers. Now, in reliable transport, the receiver will also send an acknowledgement back to the sender, notifying that the data has arrived. Let's get a closer look. So, when the sender is ready with its data, it will create a work request and post it on the send queue. This will create a work queue entry pointing at the data we want sent. And when the hardware sees the entry, it will access the data and send it on the wire. It means it is on the way to the receive side. The hardware will also generate a completion queue entry on the completion queue. And the software checking on the completion queue will get a notification in the form of a work completion. This means that the send has been completed successfully. The second type of RDMA operation is RDMA write. This is a one-side operation. It means that the sender initiates the operation and the receive side software remains uninvolved. When the send data is ready, a message is created containing the data and the location on the remote side where it should be written. When the data arrives at the receive side, the hardware is responsible to locate that memory location and write the data to it. Once the data is written on the receive side, the hardware proceeds to send an acknowledgement back to the sender to notify that the transfer is complete. Now let's take a look at it in more details. When the data arrives at the receive side, we first look at the memory registration and the data that should be written to it. If permissions allow, the data will be written to that memory location. The hardware then sends an acknowledgement back to the sender and notifying it that the operation has been completed. The third type of RDMA operations is the RDMA read. And like RDMA write, this is a one-side operation. But in this case, the data lies on the receive side. When the sender wants the data, it issues a message containing the location and the length of the data that it wants. When this message reaches the receive side, the hardware is responsible to read the data and send it back to the sender. Now, let's see how it works. When an RDMA read message reaches the receive side, the hardware first looks at the memory registration where the data resides. If permissions allow, it takes the data, reads it, and finally sends it back to the sender. The fourth and final type of RDMA operations is the atomic operation. This relies on the hardware capabilities to do several steps without any interruptions. Currently, the hardware supports the capabilities for fetch and add and compare and swap. Fetch and add has two steps. First, we fetch the current value of a number, then we increase it by a different number. Compare and swap also has two steps. First, we compare the current value, and if it matches, we replace it with a different value. Similar to read and write operations, atomic operations are handled by the hardware on the receive side. When an atomic operation arrives, the hardware first checks the memory registration for the destination of that number. If permissions allow, the atomic operations are executed. So you probably ask yourself, why do we need atomic operations? So let's use an analogy. Let's say you're making a soup and you taste it and it's missing some salt. Lucky for you, there's some salt in the other room. So you walk over and get it. But meanwhile, your roommate, who tends to taste everything you make, when you're not around, comes to the same conclusion and goes looking for the salt as well. When you return, you add the salt, making the soup perfect for your liking, and you go on with your day. But then your roommate comes back. He's unaware that you have already added salt to the soup and adds some more. Now the soup is too salty. So imagine you could taste and add the salt simultaneously. This is what an atomic operation is. It prevents interruptions from occurring between the time you taste the soup and the time you add the salt. It relies on the hardware capabilities to do several steps without any interruptions. So next time, just leave the salt in the kitchen. So now, let's see some code. And the first thing we'll go through is how to register memory. So, in order to register memory, you have to call the IBV-regmr function. The important argument for the functions are the address of the buffer and its length. We also specify the access flags, which are the request permissions to access this buffer, and operations supportive like atomic operations. In return, we get a memory region, IBVMR, with L key and R key fields. These two fields are translation handles used by the hardware when accessing the memory region, both locally and remotely. Memory registration is a control path operation. It means it typically happens in the beginning of the application, and then we deregister the memory when the application finishes. In order to deregister memory, we call the IBV-deregmr with the memory region we received from IBV-regmr at the beginning of the application. Another important code we should see is for sending messages. To send a message, we must first create a send work request and then post it on the send queue. A send work request will contain the buffer we want to send and the type of operation we want to use. Now, it's depending on the type of operation. Sometimes we need to specify additional parameters. Now, once we post the operation on the send queue, it is considered outstanding until the hardware generates a completion for that work request and posts it on the completion queue. We shouldn't access the send buffers until they are completed. Now, in order to specify buffers for sending, each buffer has to have a scatter-gather entry, what we call IBV-SGE. Each scatter-gather entry contains the address, the length, and the local key for that buffer. The local key is the result of the memory registration of that buffer. And once the work request is ready, we post it by calling the IBV post send with the QP and the send work request we've prepared. Now, a few important parameters of that work request will include the work request ID, which is a user identifier for that request. We also need the scatter-gathered list and the amount of its elements. Finally, we need the opcode, which indicates the type of RDMA operation we want to use. If we use RDMA read or RDMA write, we also need to specify the remote address and remote key. The remote address is the address of the remote buffer we want to access, and the remote key is the result of the memory registration on that remote buffer. Now, if we want to use atomic operations, we need to provide additional values. For example, values to compare the number to and to swap the number with. Now let's demonstrate how we can receive messages in RDMA. So, in order to receive messages, we must first allocate buffers for the data to be placed in. Then, we're going to create a receive work request and post it on the receive queue. And when the data arrives, the hardware will place the data in those buffers. Now, between the time you posted the receive request and the time a work completion was generated, the request will be considered outstanding, and you should not access those received buffers. When the received work request is ready, you call the IBV post receive with the QP and the work request. Now, the work request parameters include the work request ID, which is a user identifier for that request, also the scatter-gather elements list, and the number of elements in it. Both IBV post send and IBV post receive support posting more than one work request within a single call. You probably want to do that if you have multiple work requests for performance optimizations. So in order to do that, you must form a work request list by using the next parameter in each type of work request. Let's learn how to check if a request has been completed. So just a reminder, when the hardware completes a work request, it generates a completion queue entry inside a completion queue. The contents of the work completion depends on the type of the request and the status. For example, for a send completion, for reliable transport, it means that the data has arrived to the other end and has been written successfully. In contrast, for unreliable transport, it only means that the data was sent successfully and may not have reached its final destination. Now, for receive work requests, it means that the message has been written to one of the receive buffers. If the message is smaller than the receive buffers, it means that the rest of the buffer remains unchanged. So, how do you check a completion queue? You call IBV poll CQ with the completion queue, the max amount of entries you're accepting, and the array for those entries. Each work completion contains the work request ID that identifies the request completed, the status of the completion, and the opcode for the original request. In some cases, depending on the status, other fields may be filled. For example, the vendor error field will be filled in case of an error with a vendor-specific indicator. Now, here are a few typical completion statuses. Work completion success means the operation has been completed successfully. Work completion local length error means that it's likely that one of the scatter-gather elements had an incorrect length parameter. Local protection error means we exceeded the bounds of one of the memory registration we made. Work request flush error means that a different work request has finished with an error, but as a result, this one finished with an error as well. So another one is retry exceeded. It means that we've sent data to the other side, but we didn't receive acknowledgement for it. So we tried again and again, but eventually we gave up. Receiver not ready is very similar to retry exceeded. Receiver not ready means that we sent the data to the remote side, but had not received any buffers to accommodate the data. So we get a notification. And also we tried sending it again and again, but eventually we gave up. Okay, so we saw some RDMA code examples, but we cannot really use those before we establish an initial connection with the other side. So just a reminder, connection-oriented transports require a connection establishment between the two hosts before the data could be sent. So each side needs to have the opposite side address to establish the connection. And that leaves us with a chicken and egg problem. On the one hand, we need the address information in order to create the connection. but we also need some sort of connection to exchange those addresses. And this problem has two solutions. First is out-of-band communication. It means we use different type of transport to exchange the addresses and then create the RDMA connection. For example, RC ping-pong using TCP sockets to exchange the information like the remote QP number. The second solution is communication manager. Two of its services are address exchange and the connection establishment. Now, the following information has to be exchanged before we can form a connection. First, we need the layer 2 and 3 addresses, that is the local and global identifier, or the MAC and IP addresses. We also need the QP number, which is like the TCP port, and the packet serial number, which is like the sequence number in TCP. In addition, we need to agree on the communication details, such as the path MTU between the 2 points. Now, while exchanging addresses, we typically send additional information for the application to use. For example, remote keys for registered buffers. Different transport types require further information to form a connection. For example, RCQPs require the transmission count and the timer value. Next thing we'll cover is the RDMA CM. RDMA CM is the connection manager for RDMA. It has a user space library, not IB verbs, and a kernel space part. The API is designed to be similar to a server client in TCP. It has functions like RDMA connect, RDMA accept, RDMA bind, and RDMA listen. It also has a verbs specific API like RDMA create QP and RDMA post send. The API also has an event channel. It's created in the beginning of the application and used throughout the run. It externalizes events such as address resolution and incoming connections. Like in TCP, in order to establish a connection, the server needs to bind and listen on the port. The client needs to connect to that port. Once the connection is established, you can either use the RDMA CM API or verbs API to communicate in that connection. So you either call RDMA post send or IBV post send. You're probably wondering if there is a code example which uses the things we learned. So guess what? There is, and it's called RC Ping Pong. RC Ping Pong is a server-client application. It has a server to accept incoming connections and a client to connect to the server. First, we run the RC Ping Pong server. Now that the server is running and accepting connections, we will run the client and specify the destination hostname. As you can see, the application has completed and printed output with details about the connection. Now let's dive into the RC Ping Pong code. By the way, in this video we are using Visual Studio Code, and feel free to use your favorite editor. So this struct called Ping Pong Context contains a description of the context for the entire application. It uses familiar objects like queue pair, the completion queue, and the memory region. It also contains other verbs objects like the protection domain, completion channel, and the context itself. The function pp_init_context initializes the ping pong context for the rest of the application. First, it allocates memory for the context itself and the buffer we're going to use for sending and receiving. We place the pointer to the buffer in the context buff and the length in context size. The function IBVOpenDevice creates memory shared between the device and the application. This will allow us to communicate with the hardware in later functions. If we want to use event-based completions, we call IBV-create-COM channel. It creates a completion channel to communicate between the hardware and the software for notifications of completions. This function is optional, so if we don't want to use it, we just set it to null. The function IBV-alloc-PD creates a protection domain. The protection domain holds all the memory registration for this application and usually creates once per process. To register memory, we use IBV-regMR. Its parameters are the protection domain we just created and the buffer we want to register. Context buff contains the pointer to the buffer and size contains the length. The permissions are set to IBV access local write, which allows local hardware to read and write to this buffer. We also have other permissions not set, like the remote read and remote write, which means if remote hardware tries to access this buffer, it will not be allowed to do so. IBV-create-CQ creates a completion queue to be used with the QPs we create in the future. It accepts as a parameter the context which select a device and the maximal amount of work completions to be placed in this completion queue. It means it's the maximal number of completions at any given moment. Once we read a completion, a new completion can follow instead. IBV-create-QP creates a queue pair. The parameter is a struct called IBV-QP-init attributes and contains several attributes to be set in this QP. As we can see, it contains the QP type, and for RC ping-pong we are going to use IBV-QPT-RC, and also the CQ we created for sending and receiving. We could potentially see different CQs for send and receive operations. We also set the capacity for this QP. We set the maximum number of send work requests to 1, and we set the maximum number of receive work requests to a variable called RxDepth. We also limit the number of scatter-gather elements. A send work request or receive work request can contain to 1. This means we can only send messages with one buffer. And finally, we call IBV-modify-QP to set additional attributes to the QP and place its state in the IBV-QPS-init. This is the init state. The function destroys the context created in the init context function. The order of destruction is reversed to the order of creation of resources. IBV destroy QP and IBV destroy CQ destroy the queue pair and the completion queue respectively. You must first destroy the QP since it uses the completion queue. IBV deregMR deregisters the memory region we used for sending and receiving data. Only then we can deallocate the protection domain which contains all the memory regions. If we use the completion channel, now would be the time to destroy it by calling IBV-destroy-COM channel. Only then we can call IBV-close-device and close all the links to the hardware device we used. Finally, we free the memory we used to allocate the buffer and the context itself. RC ping-pong is an application that measures the performance of the connection between two hosts. First, the client sends a message to the server, then both client and server enter a loop. For each iteration of the loop, every incoming message is sent back to the sender. After a certain amount of iterations, we compare the time it took for those iterations to the number of iterations, and then we calculate the performance of the connection overall. Now let's see how RC ping-pong posts, sends, and receives requests. In this function, we post-receive requests on the QP. The parameters are the ping-pong context and n, the number of buffers we want to post for receiving. First, we create scatter-gather element with the address and the length of the buffer we want to use for communication. L key is the local key in the memory registration for that buffer. Next, struct IBV receive work request contains work request ID, which is ping-pong receive work request ID, and sglist is a pointer to the scatter-gather element we defined before. Next, we call function IBV post receive n times, every time we pass the QP and the work request we created. Note that we use the same buffer in every receive request. We can only do this because we are measuring performance and not actually sending important data. If we had sent data, request number 10 would overwrite the data from request number 9. In this function, we post a send request to the QP. First, we define the same scatter-gather element with the address, length, and the local key of the buffer we want to use for communication. Next, we define struct IBV send work request with the work request ID, which is ping-pong send work request ID. The scatter-gather list is the same scatter-gather element we define. Opcode is IBV work request send. It could have been RDMA read or write. Send flags are IBV send signal. These flags indicate we are interested in our work completion once the hardware completes the send. Then, we call IBV post send with the QP and work request we define. This is part of the code running on both server and the client. First, the client starts by sending the first message to the server, starting the ping-pong. Next, getTimeOfDay is used to measure the current timestamp before the main loop starts. The main loop will run while the number of completed receive and send requests is below the number of planned iterations. In every iteration of the loop, we start by checking the completion queue. We do it by calling IBV poll CQ with the completion queue and up to 2 expected work completions. For every work completion, we first check the status. If the status is not IBV WC success, that means that the corresponding request was failed. In this case, we print the error and exit. Assuming the work request was successful, we check the work request ID. We check if it was a send work request or a receive work request. For send work request, we only increment SCNT, which is the variable indicating how many successful sends have we completed. For receive work request, we also check the number of outstanding receive work requests. We use ppPostReceive to post additional receive buffers when the number of outstanding buffer is lower than or equal to 1. We always want the number of outstanding requests to be equal to Rx depth. That's why we pass Rx depth minus R out to post receive. If the number of send completions is lower than the number of planned iterations, we send the next message by calling ppPostSend. Finally, when the main loop over, we take another timestamp and compare it to the timestamp we took before the main loop started. By comparing the time differences and the number of planned iterations, we can calculate and print the performance of these connections. RC Ping-Pong uses TCP communication to exchange addresses of QPs between the server and the client. We will focus on the QP creation and connection establishment rather than the TCP communication. Once the server and the client have the addresses of each other's QPs, they connect the QP and start the main loop. In this function, we take the information of the remote QP as well as the local QP itself as a parameter. We take the QP which is currently in an init state, and transfer it into RTR state, ready to receive. We do that by calling IBV modify QP with the QP itself and the struct IBV QP attribute, which contains the attributes you want. Notable attributes include the QP state, which is IBV QPS RTR, and the path MTU. MTU stands for Maximum Transmission Unit. This is essentially the size of the packets sent on the wire. If you're sending a message longer than MTU, it will be broken down to pieces with a maximum size of MTU. Other features include the destQP_num, which is the destination number of the QP on the remote side. This is somewhat similar to TCP ports. Next, we transfer the QP from RTR state to RTS states. RTS stands for ready to send. We do that by calling IBV modify QP again, with the QP itself and a different set of attributes.
RC Ping Pong is a simple server-client application. It uses one QP on each end to measure the performance of the connection. To understand RC Ping Pong better, we're going to make a change to it. We're going to make it use two QPs instead of one on each end. We're going to go over the code, see the changes, and understand how they affect the run of the application. You can either try to make them yourself first or follow along this video. The first change we'll make is the work request IDs. Now that we move from one QP to two, we've moved from 2 work request IDs to 4, 2 for each QP. We have the receiver request ID and the send work request ID. Previously, just 1 and 2, but now 1, 2, 4, and 8 appear. Notice that the numbers are not one after the other, but powers of 2. This is in order for them to be used as flags for a future variable. The next change will be the address. Now that we have 2 QPs instead of 1, I've added QPN1 and QPN2 to the structure, describing the destination address. The function connecting the QPs now connects 2 QPs instead of 1. Note that it uses the same structure on both QPs. Struct IBV QP adder. With only one change, the field destination QPN1 changing from QPN1 to QPN2 between the 2 calls on the different QPs. Also, the functions exchanging addresses for the client and the server both need to change to pass 2 QP numbers instead of 1. Both the init and closed context functions are changed to accommodate both QPs. The 2 QPs are created with the same structure, struct IBV QP init adder, and the same attributes. This means that they share the same completion queue. That means when I post requests on either QP1 or QP2, the completions will arrive to the same completion queue. This also means we can use one call to IBV call CQ to check completions on both QPs. Our change to RC Ping Pong is such that the ping pong cycles are in sync between the 2 QPs. This means that we wait for both receive requests to be completed before we start the send requests on both QPs. Our changes to post, receive, and post send are that they post requests on both QPs one after the other. They use the same work request structure, with one exception, the work request ID. Before moving from QP1 to QP2, we changed the work request ID from work request ID 1 to work request ID 2. This way, when the completion happens, we know which QP was involved. Lastly, the main function holds the most changes moving from one QP to 2. This parameter called pending indicates which work request IDs are outstanding. This basically tells us which work request IDs have been posted but have not yet been completed. Every time we check for completions by calling IBV policy queue, we look at the status and the work request ID of the completed request. For send work requests, we only increment the counter. For receive work request IDs, we go to the respective QP and add additional receive work requests. Finally, we indicate this work request ID as no longer pending. Once we have no more pending work request IDs, we start the ping-pong cycle all over again by sending the next message. Now that we have made changes to creation, connection establishment, and data path of our C ping-pong, it is able to use two QPs on each end to measure the performance of the connection.